Hey guys, my name is Hiraku Murakami. I'm back with NovaEdge Academics. Today we'll be continuing with topic A5 Relativity. This is part 2. We're going to start off from time dilation actually. We covered, just to recap, we covered until last video about Lorentz transformation. We also covered Galilean relativity, but Lorentz transformation, the whole idea of Lorentz transformation was to try and relate two different perspectives for the same event. So one event happens. For me, it might be 5 kilometers away and it happened 5 seconds ago. But from another person's perspective, it might have happened 10 kilometers away 10 seconds ago, right? So these are the things that we covered in Lorentz transformation. Now, I'm going to explain to you about time dilation. And there's a famous movie called Interstellar that maybe you have watched, maybe you haven't, but it's about an astronaut essentially traveling outside of the Earth to try and find somewhere else that's habitable. And when essentially what happens is he ages a lot slower when he's on the rocket because the rocket is traveling at very close, very high speed. Turns out, his kids become older than him and they pass away. And so this whole concept of time dilation is explored in this movie where he is essentially like time traveling, because by the time he meets his child, his daughter, the daughter is actually like a grandma, like is just way older than him, and he hasn't aged quite a bit. So essentially the whole thing about time dilation is time flows slower on rocket than on Earth. And you might be saying, whoa, that's such a wild concept. And in special relativity, this makes sense. So I'm going to actually use Lorentz transformation and basic math to actually prove it to you that time dilation exists, okay? So suppose there's Earth, of course. Suppose I have someone on Earth that's watching rockets going from this point to this point. Okay? From Earth's perspective, this is happening at T1, and the rocket gets there at T2. Of course, from Earth's perspective, this is happening at X1 and X2. So it goes from X1 to X2. So the time that it takes for the rocket to go from position X1 to position X2 is equal to delta T is equal to T2 minus T1. By the way, this is from the perspective of someone on Earth. From someone on Earth that's watching the rocket go from position X1 to X2, it took T2 minus T1 seconds. Okay? Now let's put someone from the perspective on the rocket. Okay? I'm an astronaut on the rocket. What am I measuring? Well, I'm going to be measuring the same thing. I get from this position to this position, right? What's going on, right? So when I get to X1, I press start watch. And then when I get to X2, I press start watch, finish, right? Now here's one thing. X prime 1 is actually the same thing as X prime 2. Remember that X prime is the position of the rocket relative to me. The position of the rocket relative to me, well, we're traveling together, so it's always going to be 0, right? Because me and the rocket are 1. We're traveling together, so we're always going to have the same position relative to each other. So x1 is equal to x2 prime. X1 prime is equal to x2 prime, right? Now t1 prime, I can actually use Lorentz transformation. So t1 prime is equal to Lorentz factor times it by t1 minus by v x1 over c2 and c squared. I can also do the same thing for t2 prime. T2 prime is t2 minus vx2 c squared. So basically what I'm trying to get to is delta t prime is equal to t2 prime minus t1 prime. And if these two things don't align with each other, if they are not equal to each other, then there's some sort of time dilation, right? Because if delta t prime is not the same thing as delta t, basically I'm saying that we cannot agree on basically the time frame of things happening, right? For me, the rocket travels, let's say, in 10 years. But maybe from the perspective of someone on the rocket, it takes maybe 5 years, right? So I'm going to prove it to you mathematically, right? So this, let me plug in these expressions. This is T2 prime, T1 prime, right? Let me erase that so we have more space. And now it's all about simplification. So I factor this out, rearrange it. Let me factor that out as well. Now here's one more thing I can write, which is that x squared minus x1 is equal to v times t2 minus t1. Because essentially this is delta x, delta t. And velocity's whole definition is delta x over delta t. Right? So this expression holds. I hope you see that this expression holds. Right? So let me replace here with this guy. Okay? I actually need a bit more space. Okay, I'm gonna go to the next page so you can see it. Okay. Make this a bit easier. I get t2 minus t1 minus v squared over c squared t2 over t1, t2 t1, and I hope you can see I can factor out t2 minus t1 as well, and get to 1 minus v squared over c squared. Okay, so that's where I'm at. One more thing to note, this guy is actually equal to 1 over Lorentz factor squared. I can show it to you quickly, but Lorentz factor squared is equal to this squared, right? So 1 over 1 minus v squared over c squared. Flip this. Boom, right? So this expression right here. Okay, so that's going to be leading to boom. That's the final expression. So essentially what I'm saying, okay, the final expression here is delta t prime is equal to 1 over the Lorentz factor delta t. That's something I get at the end of this math. I know it was a lengthy math, but I'm trying to show it to you using Lorentz transformation, that using relativity concepts, there's something called the time dilation, where the time that I experience on the rocket, okay, is different from the time that's recorded on Earth. On Earth, the stopwatch records, let's say, 5 years. But on the rocket, I'm actually going to record 5 years divided by the Lorentz factor. So if I'm traveling at half the speed of light, we know the Lorentz factor is 1.15 when we're traveling at half the speed of light. So that's just going to be equal to 5 years divided by 1.15, which is 4.35 years. Okay, essentially saying on the rocket, my clock shows I've spent 4.35 years, but on Earth it's recorded 5 years. So this is a whole concept of time dilation, where the time that I record on the rocket is different from the time recorded on the Earth. And this is not something that's due to like a clock malfunction or anything. This is the same with biological clock as well. So I'm going to age slower on the rocket than I will be on Earth, because 5 years on Earth is equal to 4.35 years on the rocket. So if you take it to the extreme, like they did on the movie, the guy on the astronaut, right? For like 1 week, it was like years on Earth. 1 week spent on the rocket was like years and years on Earth. Okay, so that's the whole concept of time dilation. Now, if I rearrange this, I get this expression. Okay, I get this expression where essentially this guy is the delta t prime, and it's actually called the proper time. Okay, and delta t here is delta t. Okay, so delta t naught is actually called the proper time, and this is the time frame measured by the clock that is present at both events in the same location. Okay, what does that mean? This is actually really important when I get to length contraction, and so that you don't get confused which one is which. So bear with me for a second. What do we mean by that is the clock that is present at both events in the same location? Well, there was 2 events we recorded. One event was getting to here, right? Second event was getting to here. We were trying to find the time difference between those 2 events, okay? And the clock that was in the same location is basically the clock that was in the same location with the rocket, with reference to the events. So me as an astronaut with the watch on the rocket, from my perspective, my position has not changed. I am in the same location because remember, x prime 1 is equal to x prime 2. I am, regardless of whatever time that occurred, for me, I am with the rocket, so I have not changed my position. Okay, but from Earth's perspective, I have gone from x1 to x2. Do you see that difference? I hope you do, because the proper time, or t naught, is the time recorded with the same location. So it's going to be me on the rocket. And this is a very important distinction. Okay? So let's do a practice problem to incorporate this and try to solve this problem. So pause the video and give this one a try. Okay, so let's do this. So first we have to find the Lorentz factor, actually. So the Lorentz factor is going to be equal to 1 over square root y minus v squared over c squared, which is 1.34. Okay, so let's solve the problem. So delta t is going to be equal to the time dilation is equal to this, right? So now it's important to determine what is which one is which. So when I say the rocket carries a clock which ticks once every second, that's actually the proper time. And so I'm going to be able to do 1 second here, which is just 1.34 seconds. So with 1 second that's passed on the rocket, on Earth, time has passed by 1.34 seconds. Okay? And also, whenever you always get confused about which one is proper time and which one is a dilated time, I want you to always remember that the time on the rocket is always smaller than the time on Earth, or the time on the moving object that's faster is moving slower than the reference point. Okay? Now I'm going to talk about length contraction. Okay, and length contraction builds on top of time dilation. Because right now we're saying that we cannot agree on the time spent from one event to the second event. Okay, so I'm going to give you a perfect example to demonstrate this length contraction. Okay, so length contraction. So from Earth's perspective and from the rocket's perspective, we can agree on the relative velocity, right? So I can say that the rocket is going to the right relative to Earth at a certain velocity. So we can agree that it's going at velocity v. Okay? So for both of us, if the velocity is the same, but this delta t portion is different, then delta x has to also be different, meaning the length, the displacement has to be different. Okay? Now, this is from perspective of Earth, and this is from perspective of the rocket. So first of all, the time taken for me to go from Earth to Mars, okay, that's going to be equal to delta t naught. That's the proper time recorded on the rocket. But from Earth's perspective, delta t is this due to time dilation, right? Now from the Earth's perspective, we can also see the length as equal to L naught. So velocity is equal to L naught over this, right? Now, from the rocket's perspective, this is actually just, okay, let me just denote it as L. Velocity here is L over delta t naught, okay? And so essentially, what I'm trying to do is relate between the two things. If the velocity has to match, then these two expressions have to match. If I try to relate those two, I get that L naught over this is equal to L over this. I can cancel these on both sides, and I get, let me put it on here, L naught is equal to L times this, or L is equal to L naught over Lorentz factor. This is what you will see in your data booklet. Okay, so what I'm trying to show you is, because we can agree on the relative velocity, but now we cannot agree on the time, right? Now because there's time dilation, then the length also has to be different. So how does it differ? Well, from the perspective of the rocket, the length looks contracted. L here is smaller than the proper length. By the way, this guy is called the proper length. Okay, this is extremely important. Now I want to talk about muon decay experiment. So the the question that I get from students is, have we confirmed this whole point of time dilation, where we experience different flow of time from different perspectives? And the answer is yes, actually. So we've done more recently when we've developed GPS satellite system, where a satellite can carry the same identical clock on Earth, and it rotates around the Earth, okay, at very high speed. And we see about time dilation of about 38 microseconds per day delay. Okay, so we actually see that time is different. This is a very small difference, right? But it's quite significant. And then we also see in another experiment where we use a plane instead. Okay, so we put the identical same clock on a plane. The plane just jets and comes back, and we see that the two clocks, when we compare, one has a more delay over the other in like nanosecond scales. So they're very, very small, so we don't know this in everyday life. But here's the thing, the first experiment that's confirmed it is called the Muon decay experiment. And this is something that they use a Muon's decay rate to confirm relativistic phenomena. And you might be like, okay, what is a Muon, or what is a decay rate, right? It's something that we cover in later topics. So this is actually one of the things that I don't really like about the new curriculum of IB Physics, is they just chuck in stuff from later topics and expect you to learn it on the spot. So I'm actually going to use an analogy to help you understand what Muon decay experiment does. Okay, so instead of a muon, it's a particle, by the way. Muon is a particle. So instead of a muon, I'm going to use a mouse. Okay, and in a lab setting on Earth, we have discovered that mouse life expectancy is 2 years. So mouse on average lives 2 years. Okay, if you have 100 mice, okay, probably half of it is going to die in 2 years, and the other half in the latter 2 years. But most of them are going to have like a normal distribution around the center of 2 years. Some might live past 2 years, like 3 years. Some might die before 2 years. It's an average, right? Okay, perfect. But what's important is a life expectancy is 2 years. Okay, or we actually call that half-life. Okay. Now, imagine that the mouse does not take fall damage, and we actually just plop it from the top of the mountain and let it accelerate close to the speed of light. Okay, and let's say it takes 2 years to get to the bottom of the mountain. If it takes 2 years to get to the bottom of the mountain, what do we expect? We expect that about half of the mouse has died, right? Because it has a life expectancy of 2 years. So by the time it gets to the bottom of the mountain, they've already died, half of them, right? So that's what we expect. But turns out the scientists that's done this experiment discovered that a lot more than half of them lived. So in fact, let's say like 80% of them were still alive by the time they got to the bottom of the mountain. Mind you, like I'm assuming that they don't take fall damage, right? They don't die from impact. But I'm saying that when they got to the bottom of the mountain, there was a lot of them still available, which means that their biological clock, which slows down with time dilation, has managed to live more than 2 years from our perspective. But for them, it might have been, let's say, 1 year. They might have experienced 1 year due to time dilation. And this experiment basically proved the concept of time dilation because it's not just like malfunctions on clocks or anything like that. It's about biological clocks as well, right? And then now, if I replace the mouse with a muon particle, okay, this whole thing makes sense. Muon decays at very rapid rate. So muon is produced at above the atmosphere. So there was an observatory at the top of the mountain, an observatory at the bottom. They discovered that by the time it goes to the bottom of the mountain, they expected almost all the muons to have already died or decayed. But then they actually saw that a lot of them were alive, or they were present. They could detect them. So this whole experiment proves the concept of time dilation. Okay? And this is very important. You have to be able to explain this a little bit briefly. They're probably going to ask you in paper 1 and multiple choice. Very easy, like you can just memorize the answer. But also paper 2, they might ask you, 1 mark question. Explain the muon decay experiment, like 1 mark. So briefly, you write about the fact that the muon did not decay as expected due to time dilation. Very, very important. Next video, we're going to talk about space-time diagram, why it's useful when we add references as well. And so this is going to be really important. So I hope you stay tuned and check out our next video. Okay? So see you in the next video. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and get in touch with us. In the meantime, we'll see you in the next video.